All right, General Chemistry 2 class. This is the lecture for Friday, March the 26th. Now, I know you're probably sitting there thinking, this guy's wearing the same shirt he wore on Wednesday. Well, yeah, I don't change my clothes at all. So I wear the same shirts and pants every day. Actually, I'm recording this on Wednesday, so that's why. All right, so let's start with the announcements. Saturday night, Alex chapter 17b is due. And keep in mind, let me back up. I'll come to that later. I'm getting ahead of myself. Lab 7 next week, that's on buffer solutions. By Monday, you will be experts on buffer solutions, and you will know how to do all kinds of calculations with them. Worksheet 17, we're probably going to adjust the date on one of those worksheets. We'll see. I'm not sure when I have worksheet 17 down. I think that's Saturday night as well, because we should be done with everything you need to do for worksheet 17 in today's lecture. And then exam 3 coming up in about 3 or 4 weeks. We have a little despair, just a little bit of despair today. Play by the rules, get beat by those who don't. The experience we're giving you is invaluable. That's why we're not paying you anything. No one can make you feel inferior without your consent, but you'd be a fool to withhold that from your superiors. No single raindrop believes it's to blame for the flood. That's wise. We'll get to the carry-in part in a minute. I believe the children are our future, and that terrifies me. Success is a journey, not a destination, so stop running. It took millions of years to create something this extraordinary. You've got about 74. All right, so today, we're moving into chapter 18. I'm combining a number of topics from chapter 17 and 18. The titration pieces and the buffer pieces. So I like to talk about strong acid, strong base titrations in chapter 17. And then in 18, really want to focus on buffer solutions. So we're going to be a little bit ahead of Alex. This will give you plenty of time, I hope, to work on things. And this is what we're going to do today. We are going to spend our time working through a weak acid, strong base titration. Now in class on Wednesday, recording this on Wednesday, so today, but technically for Friday, in class on Wednesday, we walked through the calculations for a strong acid, strong base titration, and we talked about how to do buffer solutions. So by now, we've got everything we need to know to be able to work through weak acid, strong base titration calculations. All right, you ready for this? Good. So we're going to spend a lot of time on this slide. And just jump ahead quickly. Yep, that's right. Okay. So we're going to work through how to do problems and then establish the titration curve for all of these. We're going to do the calculations. If you recall, we did a strong acid, strong base titration with these exact same numbers. And so now what we're going to do is work with hydrofluoric acid. Let's see. And let me see, I need to look up the Ka of HF. All right, so these numbers may or may not be exactly what we are using. I came across this 6.6 times 10 to the minus 4th. 7.2 times 10 to the minus 4th sounds a little bit more of what I'm used to. So 7.2 2 times 10 to the minus 4th. That's the K A value I'm going to use. Now, for the acid-base titration, before we start, remember for the strong acid, strong base titration, we just had the strong acid in water. Same thing here, we just have the weak acid in water. In the lecture on Wednesday, we walked through the acetic acid acetate buffer system. And there we started with just the weak acid in water. Then we talked about buffers, calculations, and then we did the conjugate base alone in water. When we do a weak acid, strong base titration, it's almost exactly that same process. At the beginning, we have our container with our weak acid, in this case, hydrofluoric acid. From a practical perspective, it wouldn't work well because hydrofluoric acid dissolves glass. So if we had maybe a plastic container, that would work, definitely not glass. All right, so at the beginning, how do we process this? How do we solve this? All right, so that's okay. I'm just recording a lecture. 20 minutes? Okay. All right, so let's start with our pure acid and water. Sorry about that interruption. I just kind of take over the Gen Chem lab and start to record. And I just have a great time here because, hey, I'm comfortable with my company. But yeah, sometimes people come in and think, whoa, what's going on here? He's talking to his computer. But really, I'm talking to all of you lovely people out there in internet land. All right, so here we go, HF. We start out with just a weak acid in water. What is its concentration? 0.100 molar. Ka is equal to 7.2. 10 to the minus 4th is equal to x squared all over 0.100. I don't know that we need all 4 of these sig figs here, so I'll try to at least use 3. So if we ignore the x here and solve for if we ignore this x and solve for this x, let's see, 7.2 square root 0.00849. So what I'm going to do is plug this back in right here. I'm going to redo this instead of 0.1. 1000, I'm going to do, let's see, 0.100 minus this gives me 0.0085, 0.915. So my denominator I'm going to now plug in is 0.915, 0.09, excuse me, 0.0915. 0.0915. Times 7.2. And square root 0.00812. So my second iteration comes up like this. And this is going to be pretty close to the true value here. Let's see. Do one more iteration just to be sure. 7.2 times 10 to the minus 4th. 0.00813. Okay. Excuse me. Wow. This is just one of those days, huh? Video lecture heaven. This is the value of X for HF in pure water. You'll notice that, yeah, these are off by less than a factor of 1,000. So this X does come into play. I ignored it once, solved for X squared, and I got this. Then I plugged this in for the X in the denominator, solved it again for X squared, and I get this. I plug this in one more time in the denominator and solve for the X from X squared, and I get this. This is the value that we're looking for. So that is, X is the hydrogen ion concentration at equilibrium. So now what I'm going to do is find the pH, 2.090. Here's our pH. A weak acid problem. And you should be able to, here's the key. The key is really recognizing this is a weak acid problem, set it up and solve it. You've got to be able to set up a weak acid problem and solve it, because when it comes to weak, there are weak acids in water, weak bases in water, and buffer solutions. That's it for weak. Weak acid, weak base, or buffer. For weak acid, we use the weak acid reaction. For buffer, we use the Henderson-Hasselbalch. For weak base, it would be fluoride only. That would be an example of a weak base in water. Fluoride only, fluoride plus water gives, and then we have a KB that describes how we would do it. Same thing like this. So for a weak acid, standard format. For a weak base, standard format. This would be a KB, X squared over concentration. Now, what happens when we add 5 milliliters of NaOH to this solution? Do you remember what we did with our strong acid, strong base titration? Well, I'm sure you do. I mean, after all, I just recorded it this morning. We went with millimoles. So let's use millimoles for this. And by the way, if we use Henderson-Hasselbalch for buffer solutions, it goes really pretty quickly, believe it or not. So one thing so for Henderson-Hasselbalch, pH is equal to pKa plus log of, and for this case, it's fluoride over HF. It's conjugate base over concentration of HF. That's how we set it up. And how do we know that we have a buffer? Here's how we tell you. When we start titrating, we've added 5 mils of NaOH. Here's the concentration. Remember, volume times molarity gives us millimoles. Volume times molarity gives us millimoles. So for HF, it's the same, just like in our strong acid problem, it's the same number of millimoles each time. We're not changing the total millimoles that we're starting with. 40 times 0.1. The number of millimoles of HF. Now, here's what happens when we add sodium hydroxide to this system. It's different from what happened with strong acid, strong base. Strong acid, strong base, it's only H plus and hydroxide. When we add 5 milliliters of NaOH, how many millimoles is that? 5 times 0.1, 5 times 0.1 is 0.5. So we're adding 0.5 millimoles of hydroxide to this solution. We're adding this to this. We're adding 0.50 millimoles of hydroxide. What happens? We can look at this one of two ways. And this is really the key to a weak acid titration. This is exactly what's happening in the weak acid titration in lab that you've done this week. That half a millimole, that 0.5 millimoles of hydroxide, we can think of it this way. It pulls hydrogen ions out of solution to that extent. By adding hydroxide to an acidic solution, it pulls hydrogen ion out of solution. Another way of thinking of it is that hydroxide rips an H plus off of the HF. It rips the hydrogen ion off of the HF. By adding hydroxide, we are forcing the reaction to the right by this amount. And what happens? You can see where these numbers make sense here, because if we're pulling half of 0.5 millimoles of H plus out, it's stripping that hydrogen off, leaving this. Excuse me. Then what we have are these numbers. That's millimoles, and that's millimoles of our buffer solution. Excuse me. All right, now let me calculate the pKa. 7.2 times 10 to the minus fourth. Let's see, negative log of that is 3.143. All right, now I have everything I need to solve this problem. The key for buffers in the titration, we're adding hydroxide. That means that we're ripping the hydrogen ion off, leaving this. What if we took these numbers? If we took these numbers, and what if we add a little bit of H plus? If we add a little bit of H plus, what happens? Does it increase this? What happens is that we are converting this to this by adding H plus. By adding hydroxide, we're converting this into this. Those are not equilibrium. Those are forcing the equilibrium in a given direction. Adding OH forces it this way to the amount of OH we add. Adding H plus forces it this way to the amount of H plus that we add. And then this comes back and settles in on some. So in order to solve our pH, because this is now a buffer, we know it's a buffer because we have sizable amounts of a weak acid and its conjugate base present at the same time in solution. So the pH is equal to 3.143 plus the log of 0.500 all over 3.500. Now, I know that you're asking yourself, how can we do this? How can this happen? This is millimoles, and this is millimoles. And this is concentration, and this is concentration. The reason we can do it is because this concentration is millimoles of F minus per milliliter solution. And our denominator is millimoles of HF per milliliter solution. In other words, milliliters of solution simply divides right out. We can convert to molarity, but we don't need to. All we need is the millimole or mole ratio of this to this. We need the proportion of one to the other. That's it. So we can use millimoles directly, and by the way, the units cancel out as well. Notice what we did. It's a shift from one to the other. Now we have some of both. And because now we have some HF and F minus, and did we add any more fluoride in any way, shape, or form? No, all we did was add hydroxide. So by adding hydroxide, it simply converts HF from one form to another. We haven't changed the total amount of fluoride present. So now all we do is do the calculation. Take the log of this. The log of this will be a negative number. All right, first time, let's go ahead and do this. 0.5 divided by 3.5. And we'll take the log of that. Minus 0.845. Minus 0.845. This minus that is our pH. And our pH is 2.298. At 5 milliliters addition. Now, what I would recommend is that you have worksheet 17 in front of you and work through this calculation. I believe worksheet 17 is the same thing that we're doing. Now, that is for 5 milliliters. How does this work? Let's just jump down here to 30 mils. If we had 30 mils, so we did 5, I'm going to skip 10, I'm going to skip 20. Let's jump to 30. The number of millimoles of HF we start with is 4. The number of millimoles of NaOH that we're adding is 30 times 0.1, or 3. 3.000. By adding, so we're starting with 4 millimoles of HF and 0 of this. When we add 3 millimoles of hydroxide at 30 mils, 30 times 0.1 is 3 millimoles, we are ripping, NaOH is ripping hydrogen ion off of 3 millimoles of HF, converting it into this. We're losing this, we're gaining this by adding hydroxide. We're left with 1 and 3 millimoles respectively. So how do we find the pH? We put these numbers in here. I could add the rest of the zeros, but you can see it's a relatively simple calculation at this point. This is how you do these calculations at every volume between after 0 and before 40. After 0 and before 40. That's it. pH equals pKa plus log of anion over, conjugate base over weak acid. At this point, I would urge you to go ahead and work through all of these calculations through 39.90. Do each one, it should go fairly quickly for you. And I'm going to move right on to the next page where we have the answers. .09, 2.30, you should get these numbers going down. So for 30 mils, 3.63. For 39.9, all the way up to 5.75 for the pH. For, I'm going to put an X by the ones where we use Henderson-Hasselbalch. We use Henderson-Hasselbalch here, 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 and here. And the reason we use Henderson-Hasselbalch, this equation, is because now we are in the buffer region. Now we have sizable amounts of HF and F minus together in solution. We don't use Henderson-Hasselbalch here because it's just a weak acid only. We won't use Henderson-Hasselbalch here because when we have added 4 millimoles of hydroxide, all 4 of those millimoles of HF are now converted into F minus. So let me just write it back up. HF goes to H plus and F minus. We started with 4.00 millimoles. We add at 40 mils, we've added 4.00 millimoles of NaOH. So that what we have is HF going to 0. We don't have any more left. All of this has been stripped of its H plus, leaving us with F minus. Now, what we have is a weak base problem. We have only F minus and water. This is just like how we did these salt calculations on Monday. And if you want to go back through and review that video, how we do the calculations for fluoride ion plus water, we did this with cyanide and water. How we do those calculations, it's a weak base plus water, and we have to write it as a weak base reaction now. F plus H2O. At 40 milliliters, all we have is 4 millimoles of this in water. That's it. Weak base. There are only two reactions for weak acid and weak base. That's it. Now we're using weak base. I'm going to probably be writing over these blue numbers here. I hope that's not too much of a distraction. Actually, let me go back to the previous slide. Okay. 4.00 millimoles. For a weak base problem, I need a Kb. Well, we know that Kb is Kw over Ka, because the Ka for HF times the Kb for F minus is equal to Kw. Kw is 1 times 10 to the minus 14. So let me do that calculation quickly. 1 times 10 to the minus 14th divided by 7.2 times 10 to the minus 4th. (1.39 times 10 to the minus 11th. Let me just count my zeros here. 6, 7, 9, 10, 11. Yep, 10 to the minus 11th. And this is equal to x squared all over. Now, is it all over 4? Is it all over 4? What goes in here? Is it millimoles or is it molarity? In equilibrium, it's always molarity. The original concentration of HF was 0.1, but we've added 40 milliliters of NaOH at this point to the 40 that we already started with. We now have double the volume, or 80 milliliters. We have 4.000 millimoles of F minus in 80 milliliters solution. So instead of 0.1 molar HF, we now have 0.05 molar F minus. So this number down here, (0.0) equals x squared all over 0.05. All right. So let's do this calculation together. We know the Kb. Let's solve for x from x squared. So this is point. Wait a minute, I didn't do that right. 1.39. Oops. I need to be clear with this. I've got some weird calculation going on in the background. So I hope this comes out okay. All right. This times 0.05 is equal to 6.95 times 10 to the minus 12th. Square root of that. 8.34 times 10 to the minus 8.34 times 10 to the minus 7. X is the hydroxide ion concentration at equilibrium. X is the hydroxide concentration. Let's see. So this is the POH is 6.07. So remember, this is hydroxide concentration, from which we get POH, and then our pH is 7.92. How about that? Isn't that lovely? 7.92. Okay, so let me go on to the next slide. where I had the original answers. We've got the answers here. Now here's what I want to point out. Before we add any NaOH, it's a weak acid plus water. This is a weak acid problem, which we've walked through. After we begin adding NaOH and before the equivalence point, at all of these points in here, it's a buffer problem. And we use Henderson-Hasselbalch just like we showed you. At equivalence, when we have the same number of millimoles of hydroxide as we have of the weak acid we started with, all of this weak acid has been converted into its conjugate base, and now we only have that weak base plus water, in this case, fluoride. And then we do this thing with it. We write the reaction for the weak base plus water. We use the Kb expression. We solve for X. X is hydroxide concentration and that weak base reaction. Find pOH and then find pH. So here, pH is 7.92, so that's the number that we came up with. All right, the last step. How do we calculate pH after equivalence? What do we do at 41, at 45 milliliters? So we started with, go back up now, just to free up some board space. HF, 4.000 millimoles. F minus. At 40, let's just do 45 because it'll be the same thing at 40.1 and 41, 45. It'll be the same concept. So at 45 milliliters of sodium hydroxide, we have now added 4.5 millimoles of OH. Four of the 4.5 millimoles of hydroxide went to convert this into this. So what happens is, let me just rewrite it this way. So we started with 4.000 millimoles. All of that went over here. This goes to 0. This goes to 4.000. And the cost was 4.00 millimoles of hydroxide. We added a total of 4.5 millimoles of hydroxide. 4 of the 4.5 went to drive the HF into this. What are we left with? We have extra hydroxide left over. In other words, all of the HF has been converted into fluoride. That's the amount of hydroxide we have left. How do we calculate the pH? This now is exactly like the strong acid, strong base titration. Strong acid, strong base. We have an excess of hydroxide in the solution. We have this many millimoles of hydroxide in what volume? Well, 40 plus 45. 85 mils. (85 mils of solution. So if we take the millimoles divided by milliliters, we get molarity of hydroxide. From molarity of hydroxide, we convert that into pOH and then pH. That is how you solve each of these three. Here we have an excess of hydroxide by not that much. We have 0.01. The point, yeah, we have here we have 0.01 millimoles of extra hydroxide. Here we have 0.1 millimoles because this would be 4.01 minus 4. This would be 44.1 minus 4. This is 4.5 minus 4. If we had 50, it would be 5 minus 4 to calculate the millimoles of excess hydroxide and then divide that by the total volume. That's how we calculate the pH after equivalence. And that's the goal of the lecture for today. The whole purpose of the lecture for today is to walk through how to calculate pH for each of these titrations, or for each of these points of the titration. And here's what it looks like. Here's the graph. Notice it's a little bit funky down here. That's due to some other things. But this is a plot of all the calculations that we just did with a couple of points added in to help right around the equivalence point. Okay. One thing I want to point out, this is a more true example of what a titration curve looks like. When I say true, this is how weak acids look. With strong acids, strong base, we typically start at a little bit lower pH, and then it's straight, shoots up and then over. For a weak acid, we tend to have a little bit of a tail over here. It goes up and then comes this way. And the pH is usually a little bit higher for a weak acid being titrated by a strong base. So strong acid would be more like this. Weak acid is up here with a little tail on it. Now, the kind of curve that you see really depends on the size of your Ka value. So here's Ka of 10 to the, here's a strong acid down here. See, straight across, boom. A Ka value of 10 to the minus 2, that's still pretty acidic. Not that much higher. But when we get to Ks of 10 to the minus 4th, now we start to see that tail, and it's a little bit more of a rise. 10 to the minus 6th, bigger tail, bigger rise. And notice what happens to equivalence point. Equivalence point moves way up here. 10 to the minus 8th, a little even more. When it comes to a Ka of 10 to the minus 10th, yeah, you don't even really see much of an equivalence point at all, because now you're kind of beyond the effectiveness of how a titration will work. So what you look for with a weak acid is something more like this. A little bit of a tail, sometimes a bigger tail, sometimes a smaller tail, but there will almost always be a bit of a tail for a weak acid being titrated by a strong base. If we have a weak base being titrated by a strong acid, remember a strong base being titrated by a strong acid, way up here, sharp drop, and then we tail off. For a weak base, notice we have a little bit of a tail here. It's kept it in reverse. I'm not going to talk about calculations with strong bases titrated by strong acids or weak bases being titrated by strong acids, although there's a really good example of this in your textbook. Okay, I'm going to end with just a couple of concepts here. Couple of concepts. What do we do with the polypropylene? So actually, that's what I want to do. Let me get rid of this. Rid of this. Let me see, I want to go up to where I have some space. Let's see, I need some space. Okay, I guess I'll go back here. I just want a little bit of a place to write on the board here. So with a titration, a weak acid titration, like what we just saw for our calculations here, you'll typically see something like this. And I want to point some things out on a curve. At this stage right here, at this point, we have only a weak acid plus in water. Only a weak acid, it's 0. This is going to be milliliters of OH, and this is pH. We only have a weak acid in water. At this point right here, we have equivalence. All of our weak acid has been converted to the conjugate base. This is equivalence. You got that? These 2 points. This is a weak acid plus water. This is now a weak base plus water. And we've worked through those calculations. So right here at 0, that's how you calculate it here, weak acid plus water. At 40, that's how we would do this calculation with this problem with HF. This would be F minus at 40 mils right here. Notice that after equivalence, this titration curve looks just the same as if you have a strong acid, strong base titration, because you calculate pH by excess hydroxide ion in solution. Then, what we do in here, this is the buffer region. This is the buffer region. Everything between HA and A minus here, between the starting point and the equivalence point, is the buffer region. It's everything from 5, 10, 20, 30, 35, up to 39.9. These are the buffer calculations. The buffer, let's come back to the Henderson-Hasselbalch equation one more time. pH is equal to pKa plus log of A minus over HA. Now, where are we when these two are equal to each other? When we're equal to each other. Remember that equivalence is when we convert all of this into this. Equivalence is when all of the HA gets converted into A minus. All of this becoming this is right here. But what happens if these two are equal to each other? And the way it works for this particular problem, remember, excuse me, we started with 4 millimoles of this, 4.0 millimoles of this. Well, when these two are equal, we will have 2 millimoles of each. And 2 millimoles here, 2 millimoles here. They divide into 1, log of 1 is 0. When these two are equal to each other, this whole term goes to 0, the pH is equal to the pKa, and that is what we have right here. That is the middle of the buffer region. The middle of the buffer region. And this is the point where the pH is equal to the pKa. And this is how we determine the pKa for an acid. So in lab this past week, this is what you did. You plotted this curve, or you plotted this curve by measuring pH and plotting it against milliliters of NaOH that were added. You get the pKa by looking right smack in the middle, halfway between 0 and the equivalence, and that pH that you get is equal to the pKa. This is the value of a titration curve. And I like to teach from titration curves because if you know where you are, then you know how to approach the problem. So for example, if you know that you're down in here, you've got more millimoles of OH than you have millimoles of weak acid that you started with, then you know you do the calculation by excess hydroxide. If you don't have enough, if you're somewhere in the buffer region where you've got significant amounts of each of these, the weak acid and its conjugate base together, then you're in the buffer region. If you have only weak acid, you're right here. If you have only this, you're right here. And that tells you how to do those calculations. For a weak acid at equivalence, for a weak acid titration, and at equivalence, the pH is always greater than 7. At equivalence, the pH is always greater than 7. Go back and look at the calculation of the pH at 40 mils. And what was it? 9 point something? 7.92. 7.92. So for hydrofluoric acid, this point here was pH 7.92. because of the fact this thing will slightly interact with water. It will grab a hydrogen, leaving just a little bit of hydroxide around, shifting the pH away from 7. For strong acid, strong base titrations, at this point, the pH is always 7. The equivalence point pH for a strong acid, strong base titration is always 7.00. All right. I think we've covered enough for today. I think what I'll do is talk just briefly about diprotic acids on Monday, the polyprotic acids, and then we'll stop there. All right.